Hi, everyone. Welcome to our first lesson that's being recorded for you. So this lesson is for Tuesday, March 17th. It is going to be the notes for 11-2, day 1. So you can go to your packet. You can find that exact very thing, just that guy right there. And let's get started, shall we? I'm going to pull up the PowerPoint. It takes me just a minute to figure out how to do this. So let's get this going. And here we go. So our lesson today, of course, write down the fun title because that's way super fun, is going to be about vectors in the plane. So remember how we talked about for calculus, how there's the different like lands that we are going in. And so we're still in calculus, right? But we've talked about parametric last section, and then so now we're going to talk about vectors. Honestly, today I really feel like today's lesson is very much very pre-calcy. In fact, I kind of just like taught this lesson over a couple of days in pre-calc, and so it's going to seem very familiar. And then tomorrow we'll start more with like the calculus part of it. We're going to spend a total of 3 days on this section 2. So let's get started. First, though, we got to start with a video. So let's just sit back and enjoy a little clip. Here we go. Oh, goodness, it didn't work. So silly. Here we go, guys. Enjoy the video.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
Never gets old, does it? I love that guy. So what we're going to do is just do all those like basics that we talked about that we learned from pre-calc. And I think today's lesson should be pretty fast and you'll be able to sort of breeze through the homework. So let's do this. So we want to be able to represent objects moving in a plane, just not a straight line. One of those classic questions that you always see. It says something like a particle is moving along the x-axis, and so now we're going to be able to do something like in the plane and not just on a straight line. So when we talk about this guy right here, really what I want you to add to your notes is that is basically the coordinate a comma b. And you'll notice this should be review, guys, but there are parentheses right there, right? So the parentheses say that it's a coordinate. Well, when we do that same spot, okay, we can do an arrowed quantity, and you'll notice that the arrow just starts at the origin. It doesn't have a dot on it, but it just goes to the point. It has the arrow tip on it, and then we do the pointy parentheses now for vector a comma b. So you're drawing that into your notes. And so while we are talking about all these basics for vectors, let's go ahead and write down all of our like just like definitions. So we're just going to sort of like, if you look at your note paper, it's just a bunch of definitions. So that guy right there, that vector, is called a directed arrow. He's called a line segment. There's different words for him, but he's basically just, like the vector. Okay. So that vector is exactly what we're going to be working with. So some definitions. What's a two-dimensional vector? So a two-dimensional vector is usually illustrated with a lowercase letter and then the vector symbol. I'm going to see if I can draw that slightly larger. Okay. The vector symbol, let's write in fun blue. Okay. It is going to have your letter, and then the vector symbol has like a one-pronged arrow, and it looks like that. So that's the vector symbol. And again, it's an ordered pair of real numbers. And when we talk about component form, we want to talk about the vectors being in their components. So that's when you do the pointy parentheses, and then you put a value basically for the x's and then a value for the y's. And so A and B are what we call the components. So if you do vector parentheses, so pointy parentheses, A comma B, A and B are the components. We also have standard representation. Typically, okay, so this is called standard representation. We kind of want to remember that. So this is when your vector A comma B, it's an arrow where it starts at the origin and then it goes to the coordinate A comma B. That's basically what was up here in the top of the notes, right? So what we had already written down, like right here and then right here, this is representing the standard representation where you start at the origin. So you're writing that down in your notes. So standard representation of pointy parentheses A comma B is the arrow that goes from the origin to the point parentheses A comma B. All right, the next guy that we're going to write down is the magnitude. So the magnitude, it's has a certain a notation to it. And so we did this in last year in pre-calc. I think last year in pre-calc we did like double absolute value bars, and this just has regular absolute value bars around it. And it means the magnitude or the length of that arrow. We're going to talk about just in a moment how to calculate that. But that's the symbolic representation is absolute value bars. But remember, it's not the absolute value because we're in vector land, right? So we're living in vector land. And so those absolute value bars now mean find the length of, find the magnitude. Another word we used in pre-calc was the norm, N-O-R-M. Your direction of your vector B is basically the direction that the arrow is pointing. Okay, so you've got your direction that your arrow is pointing. So that's, I don't know, pretty self-explanatory. It's probably going to be like the theta, and we're going to talk about that in just a minute. It's a little bit lower in notes. There's something called a zero vector. It's just a vector that doesn't do anything. So if you put a 0 with the vector symbol on top and you do pointy parentheses, 0, 0, it has no length and no direction. Okay, so, oh, you know how I should say it? I should say it like this: no length and no direction. You know, like right the Haunted Mansion in Calculus Land. Oh, it's funny. Don't worry. Ha, ha, ha. If you were here and I wasn't teaching to an empty room, that'd be so funny. So a zero vector is pointy parentheses 0, 0. The magnitude of the vector. Okay, so the magnitude of the vector, this is how you calculate it. So the magnitude of the vector would, it's illustrated up here. So it goes back to that first point on this slide. It's basically just the Pythagorean theorem. Guys, you're just doing the length of it. So you have your x component and your y component. You put them in the Pythagorean theorem, you figure out how big the hypotenuse is, right? So the magnitude of vector is the square root of a squared plus b squared. Your direction is going to be measured like trig functions were. So none of this seems like surprising. You're like, oh yeah, totally, of course. Okay, so your direction angle is the theta. That either satisfies being between 0 degrees and 360 degrees or between 0 radians and 2 pi radians. It doesn't really matter which one. Most of the time in calculus, right, like we're used to radians, so I'm pretty sure they'll do radians, but every once in a while they could toss the degrees in there and we'll just have to roll with it. Okay, so, there's a little bit extra. It is officially called the smallest non-negative angle, theta, that is formed with the positive x-axis. So again, you're starting at the x-axis. I don't know if you can see me all the way, but start the x-axis and whoop, just go around. Okay. The smallest non-negative angle theta formed with the positive x-axis. It's a lot of writing today, right, guys? So just a lot of fun facts, but review. It should be just like jogging memories. Be like, oh, yes, I do remember that from pre-calc. Okay, so fun vector facts. Vectors do not have to start at the origin. Okay, you can actually draw them wherever you want. It's just kind of convenient to start them at the origin lots of times. So they don't have to start at the origin. Another fun fact is that any two vectors that have the same length point in the same direction, they represent the same vector. And so let me read that again. Any two vectors with the same length and pointing in the same direction represent the same vector. So this goes back to the point number 1. You can take your vector and you can kind of like push it wherever you want to put it. It doesn't really matter. So if they're the same length and if they're at the same angle, then obviously it's the same vector. And then a third fun vector fact is that vectors have an initial point and a terminal point. Again, initial is where it's going to start. Terminal is where it's going to end. So you could just think of it as start and finish, beginning and end, like more mathy ways, initial and terminal. And so speaking of that initial point and your terminal point, that is how you actually calculate what a vector is. So if you are given two coordinates, I'm going to get my pencil back here again, okay? You'll notice that this guy right here is a coordinate, and then this guy right here is, ooh, I went off the screen, is a coordinate. So those two coordinates right there are your initial point and your terminal point. And so if you have those two things, then you can just say your vector is terminal minus an initial. They call it the head minus tail rule. So your vector parentheses will just be the x2 guy minus the x1 guy, comma, y2 minus y1. This is so super not on the slide, but I remember it from pre-calc. Remember how back, it was literally like a year ago, for our vectors, that this is basically, do you guys remember that this is basically like slope, right? Like this is the difference in the y's and this is the difference in the x's. So you could almost think of it to yourself as that this is delta x, okay? Or excuse me, delta y. This one's delta y. And then this one would be delta x. I'm drawing with the mouse. Super not fantastic, but way super fun. Okay, so just another fun thing to remember just about your quantities. Okay, so we are going to, I turned the page too quick. Can you draw a picture of this, the vector right here? So that's the tail and then that's the head. Okay, so I think that this is just sort of like a bonus piece of information so that you're going to put on the bottom of the rule on your paper. And so if you have these coordinates right here and it's on a grid, you could maybe even, you don't even have to write this in, it's pretty self-explanatory, but if you have coordinates where it's starting at -3, 1, and then it's going to 0, 5, we could take those numbers and we could subtract them. So we're going to take our 0, which is our y2, and then we'll subtract our -3. And then we'll go 5 and then take away our 1. Okay. If you get that, if you do that mathematics, you just get 3, 4. Now, just think about that for a second. If I were just to count it off, like it would totally be the same thing. So if I'm starting right here at the start, I just do the x's 1, 2, 3. And then so my x component is 3. And then I go up 1, 2, 3, 4. Obviously that works. Okay. All right. And again, you could put that wherever you wanted to. Those would be the same vectors. It doesn't actually matter where it goes. Okay. Let's go to the next thing. Okay. So we're actually turning the page now. So I'm looking at our note packet right here. So you're going to turn the page in your note packet, and we're going to asked to do a couple of things. Remember, very pre-calc, very review right now. We're not really doing any calculus with our vectors. We're just getting like the foundations back again. So then we can go do the calculus part like tomorrow. So we're going to find the magnitude and the direction angle of this vector. I might just sketch what it is. You know my motto, always draw a picture. And so this guy is saying that we are moving, in fact, -1 to the left, and then we're going up rad 3. We'll totally erase that nonsense. And then it's my job to figure out the magnitude and the direction. So magnitude is pretty easy, so we'll save that to last. Let's find the direction angle. Direction angle, a lot of times using tangents, really nice. So I could just put the y guy over the x guy. And then if you remember from trig, this used to be something, right? Rad 3 over a -1 used to be something. It used to be a rad 3 over 2 over a -1/2. And then you're like, oh my goodness, those values are like so familiar. Okay. What angle has a sine of rad 3 over 2 and a cosine of -1/2? It's totally a 2 pi over 3 or 120 degrees. And I don't know, maybe from even just drawing this first picture right here should have been like maybe even a little obvious, like, oh yeah, that should totally be it. And then what we could do is now find the magnitude. So the magnitude, we'll go ahead and do the Pythagorean theorem with the values of, here's our x value right here is -1, our y value is rad 3. So we'll do the magnitude of this vector, and that would be the square root of -1 squared plus rad 3 squared. You probably already know what the answer is. It's a 1 plus a 3, which is a 4, and the square root of 4 is 2. So we found the length of it, the magnitude, and then we found our direction angle. Okay, so now we're going to basically do the opposite of that. For example, number 2, and it says find the component form. So they've given us the length and they've given us the angle. We're going to need a calculator for this. So you can either trust me or you can pause it really fast and grab your calculator. And notice that this is in degrees, right, guys? So most of the time, our calculator is going to live in radians, but you got to switch the mode just super quick, or maybe grab your scientific calculator. That's actually probably easier. Grab your scientific calculator really quick. and then we'll figure this out. So basically we're going at a 40-degree angle, and then we have the x component, y component, and we have the hypotenuse. So we know this should look very familiar to us. X is going to be 3 times the cosine of 40 degrees. Y is going to be 3 times the sine of 40 degrees. I would toss both of those just sort of straight in my calculator, and I get the vector parentheses, right, because it's now a vector, the components, 2.298, and then 1.928. So just make sure that you can get that. You put your calculator in degrees, and then you're golden. Okay, let's talk about some vector operations. So fun, so fun. So we've got here just some stuff that we're going to work with. So vector u right here is just going to have these quantities of u1 and u2. Vector v is going to have these guys of v1 and v2. Oh, sloppy looking. And k will just be a scalar number, okay? So if you want to add vectors, it's very simple. You just add their components. So if you're going to take vector u plus vector v, you're just going to do pointy parentheses and add the 2 first components and then the 2 second components. So it's vector parentheses u1 plus v1, comma, u2 plus v2. So you're writing that cute little part in the box on your notes. Okay, if you do a scalar and a vector, it's just, I don't know, I feel like these are kind of intuitive. So if they put k times vector u, you're basically just putting the k in front of the vector, and basically you're just sort of like distributing it into each part. It's not the distributive property, but it's kind of what you're doing. So it's vector parentheses, and then it's k u1 times nope, none of those things are right, comma, k u2. And then the opposite of the vector would be like multiplying by a -1, and you just run a negative through. So that's pretty easy. And in your head, you're thinking, okay, like the example we just had a smidge bit ago, if it went over 3 and up 4, now the opposite would go left. We went right 3 and up 4. So now the opposite would be left 3 and down 4. So you do the opposite of both the coordinates, components, excuse me. Vector subtraction is basically like adding the negative of a vector. So if you do, it's just, yeah, like so obvious. Vector u minus vector v, we'll do vector parentheses, u1 minus v1, and then u2 minus v2. There's something called the unit vector or the direction vector. And basically what you're doing is you're just thinking like, oh, this vector has a certain length, but what we're going to do is we're going to like continue it on sort of like that arrow, but squash it down. So it's just super teensy meensy. So it has the right angle, but it's only 1 unit in length. And what you do to do that is you take your vector and you divide it by the magnitude of the vector. What that really looks like in actuality is putting like 1 over the magnitude in front of the vector and then distributing it in is basically what that turns out to be. And so just like I was saying, on those go on the 2 lines on your note packet, the magnitude is 1, and basically it's just the cosine of the angle and the sine of the angle is basically what happens for that. Okay, we're going to talk about now adding vectors. So when we add vectors, there's really like 2 methods that I like to do, these 2 different ways. And so one of them is the tail to head method. Personally, that is actually my favorite one because it's just so continuous to me. You place the first vector and then you just kind of like tack on the second vector. That just feels like natural to me. And so we would just draw u and vector u and then attach vector v. So the tail method, tail to head method. You might on your notes want to draw just like a baby u vector and then a v vector that you can just use. Those are not printed on your note packet, so you probably want to just draw 2 to do. And so we'll just do our vector u, and then right at the end of vector u, right at where the arrow tip is, like right here, right there. Then we'll just tack on the next one. The answer, the official name is the resultant vector. It's going to start from the very, very, very beginning to the very, very, very end. And so this, the ultimate start to the ultimate end, is my answer. So I made it in pretty purple. Isn't that cute? So this is vector u plus vector v. Now, what you're going to find is that when you do it the next method, okay, the parallelogram method, it's going to be the same answer. You're just getting it by a different way. So the parallelogram method is you put both the vectors with their tails together. So we would, and basically like from the origin. So here's vector u, and then here's vector v. And what you do is you complete a parallelogram with those 2 being 2 of the sides. So we're going to finish the parallelogram, and I just made dotted lines. And then the answer goes the diagonal across it. So the diagonal starts from their two tails, right? The two tails right here, and then goes across the parallelogram. And so it looks like this. Now, if you look at the PowerPoint, guys, check it out. This purple vector right here and this purple vector are the same, okay? This guy right here is exactly the same vector as this guy right here. It's just they got it by different methods. So they look exactly the same, which is like the point. You can add however you want to. Okay, let's do another example. Really, seriously, super low on examples today, but super great. We're going to just do some vector. In fact, if we were in class, I probably would have just let you do this by yourself because it's really that easy. But we'll just do it together. Or if you want, you can pause the video, just pause and then come back to it, whatever you want to do. Okay, if you paused, you're back. We're going to do 2 times vector u and then 3 times vector v. So I'm going to go pretty fast through this. I put my scalar in front of both of those vectors. I'm probably going to distribute first. So I get -2, 6 as the first vector and then 12, 21 as the second vector. And then boom, I just add those coordinates and I get 10, 27. That's it. Quite lovely. Part B said we were going to subtract. So basically you're like running a negative through the V vector and then adding the 2 coordinates. Or you can just think about just subtracting each one, however you guys want. Usually these are not too difficult. So I have a -1 minus a 4 and I get -5. Oh, P.S. You do not have to write this step down. That's just for me. And then 3 minus 7 would be -4. So then that's my vector of -5, -4. Pointy parentheses, of course. And then this one says, let's think about what this actually means. This means half of vector u, and what's the magnitude? This is what it's asking, the magnitude of half of vector u. So what I would do is figure out what half of vector u is first, right? That's kind of important, by distributing that 1/2 inside. So -1/2, 3 halves. And then I'm going to take its magnitude. So now remember, for magnitude, that's what the absolute value bars mean, because we're living in vector land right now. You're going to do the Pythagorean theorem. So it's going to be the square root of -1 squared plus 3 halves squared. That becomes a 1/4 and a 9/4. That's 10/4. You can clean that up a little bit by just being rad 10 over 2. And there it is. Very last slide. Look at this. We're jamming along in our notes. We're going to write some properties of vectors just so we know them. So they're saying, for the purpose of these 9 little pieces here, vector u, v, and w are all vectors. A and b are scalars. So property 1 says this. You can actually do the commutative property. I'm not even naming it on the paper, but you can flip vectors around and it's still the same addition, the same resultant vector. So vector u plus vector v is the exact same thing as vector v plus vector u. The next one, number 2, says this is basically the associative property. And so we can group them differently and still get it right. So if you have it grouped up that you're first doing vector u plus vector v, and then you're adding vector w, it's the exact same thing as doing vector u plus the group of vector v plus vector w. A third fun guy is that if you take vector u and then you add the 0 vector, you haven't changed it. That makes sense. And so you still get vector u. A fourth one says if you take vector u and you add the opposite of vector u, you're going to get the 0 vector, right? Just imagine that would make sense. What were we doing before? Like 3, 4. So if I go right 3 and up 4 and then immediately add on a left 3 and down 4, of course, I've gone nowhere. I'm right back to where I started. A fifth one is if that you take the scalar of 0 and you multiply it times the vector u, then you will get the 0 vector. A sixth one is that if you take 1 times vector u, you will get vector u. Our 7th little property here is that if you have a scalar a times, in parentheses, a scalar times vector u, you can just group the scalars together and do a times b times vector u. Another one is that if you have a sum of 2 vectors with a scalar in front of the whole thing, you can put the scalar with each one. So a times the sum of vector u plus vector v is actually the same thing as a times vector u plus a times vector v. And then our last one is that if you have a plus b being scalars times vector u, it's the same thing as like distributing the vector. So you can go a times vector u plus b times vector u. That's it, you guys. We made it through our first like little virtual learning here. It's very exciting. Okay. So this is your assignment. It is posted in Google Classroom. I have not adjusted yet the plan book, but maybe by the time you watch the video, I will. But I'll try to make everything sync up. I hope you're doing well. I miss you. And we'll just look forward to doing this, again tomorrow. So super exciting. All right, folks. So that's our lesson. I'm going to push record sometime, stop this recording sometime soon, and we'll be good. So that's it, guys. I hope you have a great day. Have fun with the homework. Bye.